So we have demonstrated that the whole numbers under multiplication is a commutative monoid. So next, we will show that the distributive laws hold in the whole numbers. So proof, let A, B, and C be whole numbers. We'll look at cases. Again, case 1 is that all 3 of the elements are 0. Then A times the quantity B plus C is 0 times the quantity 0 plus 0, which is 0 times 0, which is 0. And the sum of products, A times B plus A times C, is 0 times 0 plus 0 times 0, which is 0 plus 0, which is 0. And thus, for case 1, we have that A times the quantity B plus C is the sum of products A times B plus A times C. So case 2, 2 of the elements A, B, and C are 0. And without loss of generality, we will assume that A and B are both 0. Then A times the quantity B plus C is 0 times the quantity 0 plus C, which is 0 times C, which is 0. And the sum of products, A times B plus A times C, is 0 times 0 plus 0 times C, which is 0 plus 0, which is 0. And thus for case 2, we have that A times the quantity B plus C is the sum of products A times B plus A times C. So case 3, we will assume for case 3 that one of the elements A, B, and C is 0. And without loss of generality, we will assume that A is 0. Then A times the quantity B plus C is 0 times the quantity B plus C. 0 times the quantity B plus C is 0. And the sum of products A times B plus A times C is 0 times B plus 0 times C, which is 0 plus 0, which is 0. And thus in case 3, we have that A times B plus C, the quantity B plus C, is the sum of products A times B plus A times C. Finally, case 4, none of the elements A, B, or C are 0. And if none of these are 0, then we have that A, B, and C are all natural numbers. And thus, we have that A plus the quantity B plus C is the sum of products A times B plus A times C, since the distributive laws hold in the natural numbers. And therefore, for any 3 whole numbers, A, B, and C, we have that A times the quantity B plus C is the same as the sum of products A times B plus A times C. That's one of the distributive laws. So further, since multiplication in the whole numbers is commutative, we have that the quantity B plus C times A is the same as A times the quantity B plus C, which is the sum of products, A times B plus A times C, which again, since multiplication is commutative, this is the same as B times A plus C times A, which is the other distributive law. And so the distributive laws hold in the whole numbers. And so we have demonstrated that the whole numbers, together with addition and multiplication, is a commutative semi-ring with unity. In the context of a ring or semi-ring, unity is the multiplicative inverse. So this structure is a commutative semi-ring with unity, but is not a ring. Since no element in the set of whole numbers has an additive inverse, no element except for the additive identity, which is its own additive inverse. The additive inverse in general of an element A is the element which we denote negative A, and we read this as the additive inverse of A, such that A plus its additive inverse is the same as the additive inverse of A plus A, which is 0, the additive identity. And so additive inverses occur as pairs, but no element except for 0 has an additive inverse in the set of whole numbers. So next we'll prove a lemma. Let A, B, and C be natural numbers. Then if A plus C is equal to B plus C, then A is equal to B. So notice that in the natural numbers, which is a subset of the whole numbers, no element except for 0 has an additive inverse. And so we cannot simply subtract or do the equivalent, which is add the additive inverse of the element C to both sides of the equation, because it doesn't exist. And so we have to prove this in another way, and so we will rely on the properties of the natural numbers. So proof. Let A and B be natural numbers. And suppose that A plus 1 is equal to B plus 1, then the successor of A is equal to the successor of B, and hence A and B are the same element. So the case C equals 1 is true. So now suppose that for some natural number K, that if A plus K is equal to B plus K, then A is equal to B. Then we have that A plus the quantity, K plus 1, that if A plus quantity K plus 1 is equal to B plus the quantity k plus 1, then we can use the associative property so that we have a plus k plus 1 is equal to b plus k plus 1. And we have already demonstrated that if a plus 1 is equal to b plus 1, then a is equal to b, or in this case, if a plus k plus 1 is equal to b plus k plus 1, then a plus k is equal to b plus k. And by the induction process, the induction hypothesis rather, we can conclude that a is equal to b. And therefore, by induction, by the principle of mathematical induction, for every three elements a, b, and c in the set of natural numbers, if a plus c is equal to b plus c, then a is equal to b. This is known as the cancellation law for addition. So now that we've proven this for the natural numbers, let's now bring in the whole numbers. We'll show that for any whole numbers a, b, and c, if a plus c is equal to b plus c, then a is equal to b. That is, the cancellation law for addition holds in the whole numbers. So proof. Again, let a, b, and c be whole numbers. We'll look at case 1. Let's have c equal to 0. Then a plus c being equal to b plus c becomes a plus 0 is equal to b plus 0. And so a is equal to b. So note that this is true whether a and b are 0 or a and b are not 0. So next we'll look at case 2. That c is not equal to 0. Now we may also assume that a is not equal to 0 and b is not equal to 0, since otherwise we have that a and b are equal, each equal to 0, and we have nothing to prove. So if a, b, and c are all non-zero, then a, b, and c are natural numbers, and hence if a plus c is equal to b plus c, then a is equal to b. And therefore, for any three elements in the whole numbers, if a plus c is equal to b plus c, then a is equal to b. That is, the cancellation law for addition holds in the whole numbers. Okay, so now we have a very good idea about the algebraic structure and properties of the whole numbers. We next want to transition or build the integers from the whole numbers. And as a first step in that direction, we're going to look at an equivalence class. So let's define a relation tilde on the Cartesian product of the whole numbers with itself. And we'll define that relation by the ordered pair AB is related to the ordered pair CD if and only if A plus D is equal to B plus C. So first, we'll note that the ordered pair AB is related to itself since A plus B is equal to B plus A. So next, suppose that the ordered pair AB is related to the ordered pair CD. Then that means that A plus D is equal to B plus C. So we have that B plus C is equal to A plus D. And hence C plus B is equal to D plus A. That is, the ordered pair CD is related to the ordered pair AB. And so the relation tilde is symmetric. So now suppose that the ordered pair AB is related to the ordered pair CD, and that the ordered pair CD is in turn related to the ordered pair EF. Then A plus D is equal to B plus C, and C plus F is equal to D plus C. And so we can add to both sides so that we have the quantity A plus D plus the quantity C plus F is equal to the quantity B plus C plus the quantity D plus E. And since addition in the whole numbers is associative, we can regroup these terms so that we have A plus F, the quantity A plus F, plus the quantity C plus D is equal to the quantity B plus E plus the quantity C plus D. And so now we can apply the cancellation law for addition. And hence A plus F is equal to B plus E, that is, the ordered pair AB is related to the ordered pair EF. And so the relation tilde is transitive. And therefore, since the relation is reflexive, symmetric, and transitive, the relation tilde is an equivalence relation.